Welcome back to the Explainer. So, have you ever spent, hours chasing down a bug only to realize the code was doing exactly what it was written to do, but it just completely failed to do what the real world actually needed? Yeah, we've all been there. Today, we're exploring a massive concept that solves exactly that problem, the model principle. We're going to look at how you can prevent those accidental bugs and a mountain of technical debt by meticulously aligning your software's design with the actual reality of the domain it supports.
Okay, let's dive into this. Here's our roadmap for today. First up, we'll look at the code-to-reality gap. Second, we're going to define what the model principle actually is. Third, we'll get hands-on and see what happens when it breaks. After that, we'll uncover the hidden technical debt. And finally, we'll wrap up with how to actively manage the model in your own architecture.
Right, Section 1, the code-to-reality gap and dealing with a messy code base.
Let's contrast two scenarios. You open up a legacy inventory system. You're expecting to find clear, business-focused terms, right? Things like a product, an order, or a shipment. But instead, bam! You're hit in the face with a data processor manager, a hash map of raw strings, and a bunch of generic database controllers. I mean, how often does that happen? You go in looking for the actual business logic and just drown in mechanical jargon. It is incredibly frustrating.
Well, that frustration actually has a formal name. It's called a high representational gap. Basically, when the structure of your code deviates from the real-world domain it's supposed to support, your cognitive load just absolutely skyrockets. Because you're no longer just coding, are you? You're forced to mentally translate business concepts, like canceling a shipment, into low-level operations, like, say, deleting a key from a cache or updating a Boolean flag in some database table. And that mental translation layer, that is exactly where the nastiest bugs love to crawl into the system.
Section 2. What is the model principle? Let's talk about direct mapping.
So here is the formal definition. The model principle states that the object structure of the software should model and mirror those concepts and actions of the real world that the software supports. Okay, but what does that actually mean in practice? It means if your software manages a library, your code base shouldn't just be stuffed with generic database updaters. It should literally have concepts like book, reader, and lending. If the real-world action is a reader borrows a book, your code should explicitly have a reader.borrowBook method. It's really that direct.
And this brilliantly illustrates the concept. Think about a digital desktop spreadsheet. Why is it so universally understood by pretty much everyone? Because it's a direct model of a physical paper ledger. It perfectly mirrors the rows, the columns, the formulas, the cells. Because the software structure mimics a physical object the user already gets, the interface is just instantly intuitive. The representational gap between the software and the physical ledger is practically zero. And we want that exact same elegance in our back-end code.
Under the hood, there are actually three distinct models at play here. First, you've got the real-world system, the physical domain or business processes. Second, the mental model, which is how the stakeholders conceptualize that system in their heads. And third, the software model, your actual classes and objects. The model principle works its magic by minimizing the gap between these three steps. When you align your software directly with the real-world domain, a change in business requirements maps exactly one-to-one with modifications in your code. It's brilliant.
Moving to Section 3, hands-on, seeing it break. Let's look at semantic misalignment.
So consider a destructive database operation, like deleting an order, versus a business lifecycle transition, like canceling an order. Look, I know it's incredibly tempting to just reuse the database delete function. It technically gets the order out of the system, right? But rewiring a business cancellation to a raw database deletion is a massive trap. If the business later decides, hey, canceled orders actually need to generate credit notes or trigger notification emails, well, your code is going to fail. It worked by accident, and it will break by accident. You absolutely must define the action at the correct level of abstraction.
Here's another really dangerous trap: inferring a capability versus using explicit capabilities. Imagine guessing a product can't be gift-wrapped just because it's marked as large in the system instead of just using an explicit first-class gift-wrap field. The crucial takeaway here is the danger of inferring business logic from totally unrelated physical attributes. Whether or not something can be gift-wrapped is a distinct business rule. It's not a direct function of physical volume. I mean, fragile or direct shipped items might be small, but they still might not support gift wrap, right?
Let's trace how this kind of indirect inference completely breaks a system. Suppose your company partners with a third-party supplier who, for whatever reason, simply doesn't do gift wrapping. To hide the option in the mobile app, your back-end team hastily marks all third-party items as product size large, leveraging that inferred rule we just talked about. But wait, now your product size data is completely corrupted. Suddenly, your shipping cost calculations fail entirely because the system thinks literally everything is massive. That one indirect inference just caused a total chain reaction of failure. Now, what's really interesting about this real-world example is how terrifying it gets. This is an experience note from a smart car system. Quote, "The air conditioning controller wanted to increase engine load. It called press gas pedal. When we integrated a hill start brake assistant, the car released its parking brake while idling. Defining the operation as request engine load would have saved a garage boom barrier." Just let that sink in for a second. Because the software used the wrong semantic action, the AC literally pressed the gas pedal in the code, which released the brakes and crashed the car right into a barrier. No way, right? But that is the absolute absurdity and literal real-world danger of disconnected semantics.
Section 4. The hidden technical debt and those subtle bugs we all dread.
Violating the model principle acts as this silent tax on your whole team. First, you get high intellectual distance. Developers have to constantly mentally translate between the business domain and these artificial concepts in the code, which severely slows down feature development. Second, semantic drift. Just like we saw with the garage barrier, code that works by accident because of hidden assumptions is inevitably going to break by accident when requirements change. And third, mismatched responsibilities. The codebase just loses cohesion. You end up with massive God classes and utility bloat because there's no natural, domain-aligned place to put new features.
Section 5. How to manage the model. Balancing those constraints.
The source material gives us this really helpful breakdown for balancing our models. First up, map natural classes, but keep this to the core domain to avoid a ton of boilerplate risk and simple data access objects. Second, and please keep this in mind, avoid taxonomy. Do not create insane, deeply nested inheritance structures just because a taxonomy exists in real life. You want to inherit for behavioral, polymorphic contracts, not biology. Otherwise, you get super fragile code. Third, establish a ubiquitous language. Yes, it takes alignment sessions, but it's absolutely essential so that terms like cancel order mean the exact same thing to the developer and the product owner. And finally, use metaphors for logic. When you're building purely technical layers like thread pools or caches, use creative physical metaphors like garbage collection so the design stays intuitive.
Looking at the practical impact ratings here, quality impact and semantic precision both score a massive 9 out of 10. Domain-aligned code stands the test of time, and it cleanly maps business vocabulary right to your class names. However, mitigation complexity sits at a 6 out of 10. Why? Well, because while designing accurate models is pretty simple in theory, actually preventing developers from taking quick shortcuts, that requires solid, daily discipline.
Which brings us to our final, and maybe most important thought. Are you building a translation, or are you just writing code? The model principle teaches us that software design is fundamentally an act of translation. By building software that mirrors the real world, you create intuitive systems and you build clean, high-level facades that prevent those nasty, leaky abstractions we discussed in our last explainer. So think about how your objects map to reality today, and make sure to join us next time as we explore the single responsibility principle to see how modeling domain concepts interacts with change boundaries. Thanks for learning with us today.